Nucleophilic substitution can be described in a remarkably simple way. A compound with a leaving group, when treated with a nucleophile, typically negatively charged but not necessarily, undergoes substitution. The leaving group leaves and the nucleophile replaces it. When we look more deeply at this reaction, we find that there are two distinct ways this can happen. One of them is called the SN2 reaction. And just in case you're wondering if this is important, my answer would be, well, how about the synthesis of adrenaline? Is that important? Absolutely. The synthesis of adrenaline depends on SN2 reactions, two of them. One to make a compound that can deliver a methyl group, and the other one to deliver a methyl group to noradrenaline to make adrenaline. And is a hormone of extreme importance for survival. So, yeah, the SN2 reaction is important. In a biological sense, in a chemical sense, it's also important because it's a reaction that's widely used to make a whole variety of compounds for pharmaceutical or industrial purposes. So the SN2 reaction comes into play biologically and industrially, and to look at the two mechanisms that account for this substitution reaction in detail is extremely useful. Let's look at the SN2 mechanism. And by the way, by mechanism, we mean a step-by-step detailed description of bond breaking and bond making. That would include arrow pushing to show the flow of electrons, and would include attention to charges and attention to stereochemistry. So a reaction mechanism is the whole picture of exactly how a reaction takes place. Here's the SN2 reaction mechanism picture for substitution, a nucleophile replacing a leaving group. When we're more careful to draw this substrate, the substrate is what we start with. When we're more careful when we draw this substrate, we have to remember that this is a tetrahedral arrangement. And without saying what's attached to carbon, let me just number them. 1, 2, and 3, because they're three things and they can be different. And in the SN2 mechanism, this neutral compound reacts with the nucleophile. It's almost always negatively charged, where we picture this pair of electrons being used to form a bond. As this bond is breaking, so we go through a transition state as this reaction is occurring, where the nucleophile is partially bonded to the carbon and the bond to the leaving group is partially broken. So that would already have a partial negative charge, and now this would only have a partial negative charge. And here's a key part of the picture. As that nucleophile comes in from the backside, as we call it, that requires that the stereochemistry of the three things attached change, and they'll all line up in a plane. As the reaction continues, this is a single step. We're just drawing what it looks like at the top of the energy diagram. As the reaction continues in a single step, that nucleophile has formed a bond with carbon. The leaving group has left, and the stereochemistry looks like this. So this is our reaction mechanism. A single step, the nucleophile comes in from the backside, a bond begins to form, the leaving group begins to leave. As the bond finishes forming, the leaving group finishes leaving. And the stereochemistry has undergone inversion of configuration. That backside nucleophile has pushed these other three substituents over to the other side. That's inversion. So let's list the key aspects of this reaction mechanism and then talk about them briefly. It's a one-step mechanism. There are two reactants participating in this single step, so it exhibits second-order kinetics. The reactant rates are sensitive to how many groups are attached to that carbon. The reaction is faster when we have a better leaving group, better nucleophile, faster reaction. We see inversion of stereochemistry. So let's take a look at this mechanism in the context of these key aspects. Everything happens at once. Bond making, bond breaking. This is what we call a concerted reaction. Second order kinetics, the rate is dependent on the concentration of both reactants. If you add more nucleophile, this reaction will happen faster because there's more collisions between the substrate and the nucleophile. If you add more substrate, same thing is true. So for instance, the classic statement is if you double the concentration of the nucleophile, the rate doubles. If you double the concentration of the substrate, the rate doubles. If you double the concentration of both, the rate is 4 times as fast. It's a very straight relationship. This is second order kinetics. It proves that there are 2 separate reacting species taking part in what we call the slow step, the rate determining step, and in this case there's only 1 step. The reaction relative rates are also fairly easy to understand. When we have a methyl group that this leaving group is attached to, we have 3 hydrogens here. Those hydrogens offer no steric barrier for the nucleophile to approach that carbon from the backside. As we add substituents, going from methyl to primary, there's 1 alkyl group. Secondary, there's 2 alkyl groups. Tertiary, there's 3 alkyl groups. By the time we get to 3 alkyl groups, the steric requirement of those alkyl groups is so large that tertiary SN2 reactions do not happen. Make a note, tertiary SN2 reactions do not happen, and it's simply a result of the steric requirements of the 3 alkyl groups being attached to carbon. Better leaving group, faster reaction. Makes sense. If this leaving group leaves readily, the reaction will happen faster. If this bond is much harder to break, leaving group does not leave well, reaction is slower. Better nucleophile reaction rate, yes. The more available these electrons are for sharing, bond making, the faster the reaction happens. So what we've just said is if this bond breaks more easily, the reaction is faster. If this bond is made more easily, the reaction is faster. Both those things make sense. And then finally, notice that there's, at least formally, inversion of stereochemistry. That because this nucleophile is approaching from the back side, and these 3 substituents are forced to go from the back side through some planar arrangement like this to being over on the other side, this automatically causes inversion of stereochemistry. Now the explanation for this is related to a careful analysis of the bonding of the leaving group and carbon and this sp3 orbital that's involved. If you're looking at valence bond theory, or the MO molecular orbital bond that's involved with breaking, if you're looking at MO theory. But an analysis using either MO theory or valence bond theory brings you to the same conclusion, that for this pair of electrons to be bonding to this carbon, while this pair of electrons is still associated with this carbon, the nucleophile must approach from the backside, which leads to inversion of configuration. So there you have it, the simple SN2 reaction. It's a 1-step concerted mechanism, exhibits second-order kinetics. The reaction rates are sensitive to the steric requirements of the things that attach to carbon. The reaction rates are sensitive to how easily that bond is broken or the new bond is made. And inversion of stereochemistry occurs. After we've talked about the SN1 reaction, we'll talk about a couple of other aspects of this reaction that are worth noting. But these are the key features.